So I should like to introduce the author of our final paper, who's not here in person because of coronavirus. Not that he has it, but he was afraid of being stranded in Europe by it with nowhere to sleep. So William Carroll has been our Thomas Aquinas Fellow at Blackfriars since before there was an Aquinas Institute. He set up our annual seminar series and obtained money for it from the Earhart Foundation until they ran out of money a couple of years ago, and he organised the series for many years. And he taught in the Faculty of Theology here on science and religion. His interests are in the reception of Aristotelian science in medieval Islam, Judaism, and Christianity, and the development of the doctrine of creation ex nihilo, and how one might relate Aristotelian and medieval discussions of such issues with contemporary science. Bill lives chiefly in America, but is frequently in South America and in China to lecture on Thomas Aquinas and the issues I've mentioned, also Slovakia and other places. And he has already run 2 academic workshops, one at Wuhan, long before there was coronavirus, one at the University of Peking last year, and a third one is due at Zhejiang University on Thomas Aquinas' creation and contemporary science in November this year. So he's extremely active in spreading the word. He's written with Steve Baldner Aquinas on Creation and other things like Galileo, Science and Faith, Divine Agency, Contemporary Physics, and the Autonomy of Nature, and After Darwin, Aquinas. And it was he who conceived this particular colloquium, so we're very grateful to him. And he's written a paper for it entitled The Scientific Revolution and Aristotelian Thomistic Natural Philosophy, in which, as you will find, he offers an alternative perspective on what, in fact, Newton in particular has meant for, has it made Aristotle and Aquinas out of date, or has it not? So he's calling into question something of the perceived history of thought in this area. And you should all have a handout with the texts that are quoted. So the first text on the handout from Charles Gillespie claims Aristotelian physics made sense of the world and strengthened the hands of the men of God and all those striving to redeem civilization, culture, and truth from barbarism. There was only one problem: it was wrong. And Bill writes, in many ways we have come to understand the scientific revolution of the 17th century as a watershed event in the history of the West, as an event, or better, a series of interconnected events, which has produced the modern world. The stories we tell about what it means to be modern are frequently laced with references to the rise of modern science, associated with figures such as Galileo and Newton, or to the advent of modern philosophy with thinkers such as Descartes. There seems to be little doubt that the 17th century witnessed a turning point in Western intellectual history, a turning point which in a very real sense was epoch-making. As a result of this turning, we live, so it's often claimed, in a world irreducibly different from the one animated by Aristotelian and Thomistic thought. So distant are we, at least in conceptual terms, that any appeal to principles of science and philosophy associated with that older world is rejected. My approach in this talk is to point to certain historiographical and philosophical barriers that need to be overcome if we wish to take seriously what Aristotle, Thomas, and others living before the advent of modernity had to say about fundamental questions about nature, and indeed human nature as well. I want to examine the adequacy of the commonly accepted interpretation of the rise of modern science as involving necessarily a rejection of the science of Aristotle and his medieval successors. I want to identify a set of underlying presuppositions of modernity and science which tend to prevent us from examining a Thomistic worldview, except perhaps as a kind of idle curiosity. Ultimately, I hope to offer an opening, a kind of intellectual space, for taking seriously a concept of nature that finds its roots in Aristotle and its flowering in Thomas Aquinas. Let me begin by calling your attention to a standard rendering of what we might call the master narrative of the scientific revolution, since it's a narrative that continues to be influential. So text 1a on your handout. Herbert Butterfield, writing slightly more than 50 years ago in The Origins of Modern Science, remarked that because the scientific revolution overturned the authority in science not only of the Middle Ages but of the ancient world, since it ended not only in the eclipse of scholastic philosophy but in the destruction of Aristotelian physics, it outshines everything since the rise of Christianity and reduces the Renaissance and Reformation to the rank of mere episodes, mere internal displacements, within the system of medieval Christendom. Since it changed the character of men's habitual operations, even in the conduct of the non-material sciences, while transforming the whole diagram of the physical universe and the very texture of human life itself, it looms so large as the real origin of the modern world and of the modern mentality that our customary periodization of European history has become an anachronism and an encumbrance. Though we may be less enthusiastic than Butterfield in his characterization of the importance of the scientific revolution, we ought to recognize in his comments the prevailing view of the scientific revolution as the overthrow of Aristotelian science. We may well accept Thomas Kuhn's description of this revolution as a paradigm shift, and thus react sceptically to claims which conclude that Aristotle's science was false and modern science true, but nevertheless the master narrative remains intact, since, in Kuhn's terms, there's an incommensurability between the old and the new paradigms. We might follow Pierre Duhem, who locates the real revolution in 14th century Paris, the result in part of the famous condemnations of 1277, well, I would say infamous, and in particular in the development by Jean Buridan of impetus theory as an explanation for projectile motion. Or we might follow Alexandre Koyré, who interprets the revolution in terms of a grand metaphysical shift from Aristotelian to Platonic metaphysics, from the closed world to an infinite universe. Yet there remains little doubt that a major intellectual and cultural transformation occurred. The 2008 recipient of the Templeton Prize, Michael Heller, Polish mathematician, cosmologist, and Catholic priest, has frequently noted, and that's text 1b on the handout, that the rise of modern science has its source in a mathematical experimental view of nature, founded on premises which do not conform to and are actually incompatible with the philosophical position of Aristotle and Aquinas. Any attempt today to retrieve that tradition is doomed to failure. Sober words for what I wish to argue here. The standard version of the master narrative tells the story of how Galileo and Newton overturned the antiquated Aristotelian view of the universe and established the principles of modern science. Although the master narrative has many subdivisions, it will be useful to focus on what is regarded as the very first principle of the new physics, the principle of inertia, defined in text 2a. Every body perseveres in its state of rest or of uniform motion in a straight line, unless it is compelled to change that state by forces impressed upon it. Alfred North Whitehead called the principle of inertia the first article of the creed of science, and like the Church's creed, is more than a mere statement of belief. It's a paean of triumph over defeated heretics. The defeated heretics, Whitehead explains, are the Aristotelians, who for 2,000 years imposed on dynamics the search for a physical cause of motion. According to this interpretation, Newton's principle of inertia contradicts Aristotle's principle that everything which is moved by another. If Newton is right, Aristotle must be wrong. Contemporary commentary on the relationship between traditional theology and the natural sciences has been heavily influenced by the orthodox interpretation of the scientific revolution as a radical rupture in the history of science. Anthony Kenny, for example, denies the probative force of Aquinas' proofs for the existence of God, because these proofs are based on the principles of Aristotelian science, a science which the modern world has shown to be false. So text 2b, Newton's law of inertia wrecks the argument of the first way, for at any given time, the rectilinear, uniform motion of a body can be explained by the principle of inertia in terms of the body's own previous motion without any appeal to any other agent. And there seems to be no a priori reason why this explanatory process should not go backwards forever. Newton's law will not explain how motion began, but how do we know that motion had a beginning? In volume 3 of his A New History of Western Philosophy, Kenny argues that Galileo, Descartes and Newton were able to show that the principle fundamental to Aristotelian physics, that nothing moves unless acted upon by an external source of motion, was false. Kenny also thinks that Aquinas' ethical theory suffers because his account of appetites in man and in animals depends upon an archaic physics, now known to be false. Any notion of the natural agency of inanimate matter can't be reconciled with the principle of inertia. Newtonian mechanics, Kenny says, rules out any appeal to a teleological account of all of nature, that's text 2c. The operations of the laws of inertia and gravity and the natural activities of sulfur or uranium aren't teleological activities at all. If we today are to seek, as Aquinas did, to locate animal desire and human willing in a hierarchy of different kinds of tendencies towards good, that we must put at the bottom level of the hierarchy not the natural agency of inanimate matter, but the non-conscious teleological activities to be found in the plant world. Kenny observes that for Aquinas, all action, including the most elemental actions of completely inanimate bodies, was fundamentally teleological. This part of Aquinas' system is something which must be discarded if we are to make any use of his philosophy at the present time. Kenny admits that the liberation of physics from the erroneous principles of Aristotelian physics was accompanied by an impoverishment of philosophy. Though Aristotle's scientific physics was shown to be very largely mistaken, his conceptual scheme retained much value. All too often, both good and bad were thrown overboard together. Here Kenny suggests a useful distinction between what he calls two disciplines, a kind of broad philosophy of nature concerning general concepts such as space, time, motion and change, and a distinctly new science of physics. Nevertheless, I think that Kenny's analysis suffers because he accepts, at least in part, what I have called the standard narrative of the scientific revolution. The implications of such a view for discussion in ethics can be seen in the work of Alistair Mcintyre. Despite his sympathies for Aristotle and Aquinas, Mcintyre argued, at least in his early writings, for the necessity of providing a new foundation for ethics, different from the natural philosophy of Aristotle and Aquinas, by pointing to the encounter between impetus theory and the inertial physics of Galileo and Newton, which encounter he called a classic case of systematically different and incomparable observational languages, key concepts, and theoretical structures, which were framed in terms of rival and incomparable standards, such that there was no shared common measure between two physical systems. The epoch-making nature of the scientific revolution, and in particular of the principle of inertia, is evident in the analysis of an influential German theologian, Wolfhart Pannenberg, who died in 2014. Pannenberg claimed that the acceptance of the principle of inertia in the 17th century represents not only a radical break in the history of science, but also in a fundamental problem for the Christian doctrine of creation. Pannenberg says that the principle of inertia lies behind a denial of the radical contingency of the world, a contingency central to the doctrine of creation. Creation means that the world is contingent. Modern science denies the principle of contingency, as this science developed in the 17th century. Furthermore, as he remarked, any contemporary discussion regarding theology and science should first focus on the question of what modern science, especially modern physics, can say about the contingency of the world as a whole and every part in it. Only if science reveals a contingent universe can there be room for a doctrine of creation. For Pannenberg, it's not until the ascendancy of field theory in contemporary physics that we can discern a complementarity between the claims of physics and the theological concept of creation. Pannenberg suggested that we might think of the Spirit of God as such a total field which environs the cosmos. The idea of spirit as a universal field of energy which engenders a process of creative unification, then leading organisms to transcend themselves towards increasing complexity and structure. Although Pannenberg thought the contemporary field theory in physics, unlike the principle of inertia, does allow for a radical contingency in nature, I want to point to what he claimed to be the original significance of the principle of inertia for the doctrine of creation, since his argument here reinforces the widely accepted view of the radical nature of the scientific revolution. Pannenberg observed that it was Newton's understanding of inertia in terms of a force that is inherent in bodies, along with the reduction of force to a body and its mass, that contributed decisively in the course of the 18th century to the removal of God from the explanation of nature. And this is text 2D at the top of page 2 of the handout. The emancipation from the Creator God entailed in the principle of inertia did not apply only to natural bodies and beings, which at the same time continue to undergo influences from outside themselves. Even more serious was the consequence that the system of the natural universe had to be conceived now as an interplay between finite bodies and forces without further need for recourse to God. The source of Pannenberg's understanding of the philosophical and theological importance of the principle of inertia is the work of another German thinker, Hans Blumenberg. In two major books, The Legitimacy of the Modern Age and The Genesis of the Copernican World, Blumenberg ranged widely in philosophy, the natural sciences, theology, political thought and literature, as he examined the transition from the medieval to the modern world. For Blumenberg, the novelty of modernity is to be found in what he calls the reoccupation of prior explanations of man, nature, and God. Here's an example of what Blumenberg means. The modern commitment to human autonomy and self-assertion was, for Blumenberg, a response to the claims of divine omnipotence, of the absolute power of God, characteristic of nominalist thought. Such an affirmation of divine omnipotence entailed a denial of an intelligible order of nature which human reason could discover. The utter contingency of a world dependent upon the absolute will of God, according to Blumenberg, was a disappearance of order, which causes doubt regarding the existence of a structure of reality that can be related to man, and makes the traditional conception of human activity, bound up in the ancient and medieval cosmos, no longer workable. So, text 2E of the handout. The modern age has regarded self-preservation as a fundamental category of everything in existence, and has found this borne out all the way from the principle of inertia in physics to the biological structure of drives and the laws of state building. Blumenberg thought that the early modern mechanistic explanation of nature, with its commitment to absolute matter, reoccupies the position of late medieval nominalist mode of explanation based on the absolute divine will. Self-assertion and human autonomy are the broader cultural correlatives of a fundamentally new principle of explanation, and for Blumenberg, it was the principle of inertia which lies at the core of this new view of things. So, text F, with the principle of inertia, there is in all things, in all matter that is, an inherent force of self-preservation. Consequently, a transcendent conservation of nature becomes indeed superfluous. In a similar way, the transfer of movement renders the assumption of a divine cooperation in the activities of creatures superfluous. Thus, deism must be seen as the consequence of the principle of inertia in modern physics. There's no question, for scholars like Pannenberg and Blumenberg, that there are wide-ranging and revolutionary consequences of the scientific revolution, seen through the prism of what they consider its most characteristic feature, the principle of inertia. So in the third part of his paper, Bill discusses the principle of inertia and Aristotelian physics. If there is a fundamental incompatibility or incommensurability between Aristotelian science and modern science, then any philosophical reflection rooted in or employing principles from Aristotelian science must either be rejected or radically reformulated. Often I participate in conferences on the relationship between religion and science, in which speakers refer to the Newtonian settlement as the basis for modern philosophy and theology. This settlement tends to rule out appeals to Aristotelian and Thomistic natural philosophy, since, so the argument goes, such a philosophy of nature has been rendered false by modern science. This helps to explain why in the 17th and 18th centuries it was apparent to many that only a mechanistic philosophy of nature could meet the evidence of modern science. Indeed, early proponents of mechanism, especially in the 17th century, saw it as a way to reconcile their belief in God with the insights of Newtonian science. More frequently today, process thought is urged as providing the necessary philosophical complement to the natural sciences. Form and matter, substance and accident, teleology and the like, concepts drawn from scholastic philosophy, are thus all seen as part of a view of the world which, thanks to the scientific revolution, we know is wrong. As we have seen, nowhere is the rejection of Aristotelian physics more evident, so the master narrative of the scientific revolution would have it, than in the principle of inertia, which, so it seems, directly contradicts a fundamental Aristotelian principle that everything that is moved by another. One could, of course, discuss the denial of final causality in nature, or the reduction of qualities to quantity, but these are more specifically developments in natural philosophy. It's the principle of inertia which is the key doctrine to examine. If we turn now to the principle of inertia and examine it in some detail, we can confront the thesis of a fundamental incompatibility between Aristotelian science and Newtonian science. Such an analysis, I think, will offer evidence against the view that to accept modern science, one must reject the principles of Aristotelian natural philosophy. Before I proceed in my analysis, I want to commend to your attention a section on inertia and Aristotelian Thomistic natural philosophy set forth by Edward Fraser in his new book, Aristotle's Revenge, The Metaphysical Foundations of Physical and biological science. And that, well, just the title of that is under 3a on your handout. And please read it. Fraser emphasises that contemporary physicists speak of motion as a state rather than a change. Any supposed contradiction between these diverse senses is the result of an equivocation, the failure to understand two different categories of analysis. In what follows, I want to suggest underlying causes for this confusion. Newton's famous 3 laws of motion appear early in the Principia. He begins with a series of definitions concerning mass, forces, and the like, then states the 3 laws and deduces corollaries from them. These laws, corollaries, and definitions are expressed in expository prose without those mathematical equations with which we may have become familiar. In the preface, Newton reminds the reader that in this work he will subject the phenomena of nature to the laws of mathematics. At another place he observes that he only provides a mathematical notion of forces without considering their physical causes. He tells us that he is considering forces not physically, but mathematically. At the beginning of Book 3, entitled The System of the World, Newton notes, in the preceding books, I have laid down principles not philosophical, but mathematical. When he turns to discuss various explanations of planetary motion, he notes the ancient view of the planets being embedded in solid orbs. Newton thinks that Descartes and Kepler postulated celestial vortices as the way to account for such motion. And then he comments, from the first law of motion, it is very certain that some force is required, but our purpose is to bring out its quantity and properties and to investigate mathematically its effects on moving bodies. Although Newton was convinced of the tremendous power of mathematics to discover and describe accurately certain fundamental characteristics of the world, we must not think that Newton was some 17th century Pythagorean, for whom the mathematical description of reality is the only true scientific account of nature. Newton warns against such an attribution when he remarks, and that's text 3b on the handout, those people violate the accuracy of language, which ought to be kept precise, who interpret these words, time, space, place, and motion, for the measured quantities. Nor do those less defile the purity of mathematical and philosophical truths, who confound real quantities with their relations and sensible measures. Prior to enunciating the principle of inertia, Newton provides a definition of centripetal forces in which he hypothesizes what would happen in projectile motion if the resistance of the air is taken away. In this discussion, Newton moves from the world of ordinary experience to imagine the limiting case of motion, that at which the projectile would proceed in its motion forever. Newton describes what obtains in a limiting case, and thus he presupposes the concept of limit in the derivation of that case. Newton's notion of limit is drawn from mathematical modes of reasoning. It's precisely such a mathematical concept of limit which is at the root of the principle of inertia. The principle is an inference drawn from the mathematical physical approach to a limit. In other words, as the resistance of the medium approaches zero, the distance travelled approaches infinity. As an idealized, quasi-mathematical concept, the principle of inertia involves an abstraction from the extrinsic forces acting on real bodies, moving in a physical environment. The principle also involves an abstraction from any kind of physical causality. Accordingly, the principle of inertia, regardless of its truth, says nothing in support of, nor in contradiction to, Aristotle's principle in physics that everything that is moved by another. There's no explicit discussion in the Principia about the need for an extrinsic cause for motion, apart from what Newton says about God as universal mover. Nevertheless, in some reflections on mechanics at the end of the Optics, Newton observes what's in text 3c on the handout. The vis inertiae is a passive principle by which bodies persist in their motion or rest, receive motion in proportion to the force impressing it, and resist as much as they are resisted. By this principle alone, there could never be any motion in the world. Some other principle was necessary for putting bodies in motion, and now they are in motion, some other principle is necessary for conserving motion. The principle of inertia considers bodies simply as three-dimensional realities devoid of natures. Such an abstraction from nature is possible and appropriate in the mathematical study of nature. In an unpublished early work, Newton commented on the kind of entities which mathematical physics considered, and that's text D at the foot of page 2. Moreover, since body is here proposed for investigation, not insofar as it's a physical substance endowed with sensible qualities, but only insofar as it is extended, mobile, and impenetrable, I have not defined it in a philosophical matter, but abstracting from the sensible qualities, I have postulated only the properties required for local motion, so that instead of physical bodies, you may understand abstract figures in the same way that they are considered by geometers when they assign motion to them. In the universe in which we live, there are no nude bodies devoid of natures, and there are no bodies in uniform motion in a straight line forever. Newton's first law of motion cannot be a law of nature, least of all the prima lex naturae that Descartes thought necessary in his universe of geometrical space. Only in such a Cartesian world of nude bodies, each with a fixed quantity of matter and a fixed quantity of motion, can there be such a first law of nature. The Cartesian world, however, is not Newton's world, and Descartes' notion of inertia is not Newton's. Only if one assumes that the principle of inertia is a law of nature and not simply a principle in mathematical physics, would one have a problem with its relationship to Aristotelian physics. There are several classical texts which have contributed substantially to an overemphasis on the mathematization of nature in the scientific revolution. In what became a very famous book, The Metaphysical Foundations of Modern Science, and that's text 4a on the handout, E.A. Burt summarizes this position. We have observed that the heart of the new scientific metaphysics is to be found in the ascription of ultimate reality and causal efficacy to the world of mathematics, which world is identified with the realm of material bodies moving in space and time. Expressed more fully, the real world in which man lives is no longer regarded as a world of substances possessed of as many ultimate qualities as can be experienced in them, but has become a world of atoms, now electrons, equipped with none but mathematical characteristics, and moving according to laws fully statable in mathematical form. I have already mentioned Alexandre Koyray's From the Closed World to the Infinite Universe, in which he argues that the scientific revolution is, at its core, a fundamental metaphysical shift away from a finite Aristotelian universe of qualitative distinctions to a universe of infinite geometrical space in which physical reality is exhaustively captured in mathematical terms. Newton's principle of inertia is for Koyrey inconceivable without this change in metaphysics. Only in an infinite universe could one conceive of a uniform motion in a straight line forever. The application of mathematics to the study of motion necessarily involves an abstract world. And an abstract world is not a false world, but nor is it identical with the world of nature. Newton knew full well that when, for example, he defined mass as the quantity of matter and momentum as the quantity of motion, he was proceeding in the realm of mathematical physics. We should take a clue from the title of his work, Mathematical Principles of Natural Philosophy, which differs in a crucial way from Descartes' title, Principles of Philosophy. Along with James Weishaupt and William Wallace, whose analyses have influenced my work significantly, we should recognize that in Newton there is not so much a rejection of the principles of Aristotelian physics as a great expansion of and sophistication in the science of mathematical physics. In the tradition of Aristotle and Thomas Aquinas, physics, or the philosophy of nature, is a more general science of nature than the various empirical sciences. It concerns broad questions about the nature of time, change, and the like, and it embraces as well the conclusions of all the individual natural sciences. As Aquinas points out, the natural sciences study what exists in matter and in motion precisely as these things exist in matter and motion. Man cannot be studied as man, distinct from flesh and bones, without his materiality. Mathematics studies those dimensions and quantities which exist in sensible matter, but which can be known separate from sensible matter. Through a process of abstraction on the part of our intellect, we have the capacity to understand shapes and numbers independently from the material bodies in which they exist. Mathematics and the natural sciences can be distinguished in terms of their respective objects of study, as well as in terms of the different ways in which the objects are known. Mathematics does not provide a deeper explanation of the world of nature than does physics, nor does mathematics provide the true principles of scientific inquiry for the natural sciences. The natural sciences have an autonomy appropriately their own, with respect to theology, to metaphysics, and to mathematics. In talking about quantity, I should like to emphasize that quantity can be studied first in metaphysics as the category of being, secondly in physics as a property of substance and according to quantity's proper nature, and three in mathematics as it has certain properties that lack any order to substance, hence as nude quantity. And since sensible qualities come to substances through the medium of quantity, mathematical physics can provide some access to these features of reality. Although for Aristotle and Aquinas, mathematics and physics are autonomous and distinct sciences, one may apply mathematical principles to the study of natural phenomena. Such applications occur in neither the science of mathematics nor in physics. They constitute mixed sciences, types of knowledge intermediate between what we might term pure mathematics and a more general science of nature. Aristotle recognizes the legitimacy of such intermediate sciences, what he considers to be in some sense branches of mathematics, which come nearest to the study of nature, optics, harmonics, and astronomy. So text 4b, referring to such mixed sciences, Aquinas writes, "It doesn't belong to the mathematician to treat of motion, although mathematical principles can be applied to motion. The measurement of motions are studies in the intermediate sciences between mathematics and natural sciences." In more general terms, Thomas observes what is text 4c. So there are three levels of sciences concerning natural and mathematical entities. Some are purely natural and treat of the properties of natural things as such, like physics. Others are purely mathematical and treat of quantities absolutely, like geometry, considers magnitude and arithmetic number. Still others are intermediate, and these apply mathematical principles to natural things, for instance, music, astronomy, and the like. These sciences, however, have a closer affinity to mathematics, because in their thinking, that which is physical is, as it were, material, whereas that which is mathematical is, as it were, formal. For example, music considers sounds, not inasmuch as they are sounds, but inasmuch as they are proportionable according to numbers, and the same holds in other sciences. Thus they demonstrate their conclusions concerning natural things, but by means of mathematics. The application of mathematical principles to a study of natural phenomena is never a substitute for the science of physics, which has as its object the study of physical bodies in their full reality. Principles of mathematics, though applicable to the study of natural phenomena, can't explain the causes and true nature of natural phenomena. It seems to me that we can best understand the history of science in the West in the 14th through to the 17th centuries, and even beyond to our own time, if we recognize that some of the greatest accomplishments in the sciences have taken place in mathematical physics, the intermediate science between mathematics and physics. The developments in the natural sciences in the 17th century, most apparent in the field of physics, don't so much represent a rejection of the principles of Aristotelian physics, as they mark a great advance in our understanding of the ways in which mathematics can be applied to the study of physical reality. The sciences of Galileo and Newton, strikingly original as they are, remain fully consistent with the general Aristotelian science of nature. Once we understand the nature of mathematics, physics, and the intermediate sciences, an understanding present in the thought of Aristotle, made explicitly by Aquinas, then I think we can see a fundamental continuity in the history of science from the time of Aristotle to the present. Although ancient and medieval thinkers were not very concerned with what's called mathematical physics, and they surely didn't expect such a fruitful expansion of the role of mathematics in describing the natural world, still they did recognize the validity of the use of mathematics in investigating nature. And this perspective on the scientific revolution frees us from the false view that one must choose between Aristotle and the great advances of modern science. The philosophical baggage of a mechanistic and materialistic natural philosophy, often associated with modern science, is the product of philosophical traditions in the 17th century and beyond. Mechanism and materialism represent a radical rejection of Aristotelian and Thomistic natural philosophy. But mechanism and materialism remain excess baggage, not required in order to accept the advances in our understanding of the world, which are the legacy of Galileo and Newton. Misinterpretations of the scientific revolution may also have tempted some in the Thomistic tradition to retreat from the arena of natural philosophy to bask in the seemingly safer and ethereal realm of metaphysics. The history of science can help us distinguish among the advances of modern science, the mechanistic and materialistic natural philosophy which has accompanied these advances, and the principles of Thomistic natural philosophy, which can lead to a deeper and more complete understanding of nature, human nature, and their dependence on a creator. So if we distinguish the developments in mathematical physics from the philosophical baggage often associated with the scientific revolution, that allows us to avoid the error of thinking that the rise and development of modern science renders useless the philosophical insights of Aristotle, Aquinas, and others. I hope I've shown how a knowledge of the history of science is crucial when one raises difficult questions in natural philosophy and metaphysics. I haven't argued directly for the cogency of the metaphysics and natural philosophy of the Aristotelian Thomistic tradition, but have tried to lay the proper groundwork for continuing to take seriously the claims of that tradition. So that is Bill's paper, and I notice with great delight that he exonerates a fellow member of Trinity College, Cambridge, from causing modern problems. So, thank you.